Okay, so we're going to begin now this chapter. This chapter is all about exponential functions and logarithmic functions. The first lesson that we're going to focus on is dealing specifically with exponential growth. So let's look at this equation. Now this equation, if you notice, is for exponential functions in general. So you want to make sure that you have this formula down because this formula we're going to be using throughout these next few sections. Now the formula f of x equals a times b to the x power, that's your formula for any exponential function. A is always going to represent your initial amount, or the value that you start with. B is always going to represent your growth factor. Now today we're focusing on where b is greater than 1, so that represents exponential growth. Now some pieces about this is that a can never equal 0, because if a was 0, and you multiply that times b, you'd end up with nothing. So a can never be 0. B has to be positive. B can't be a negative number. And it also can't equal 1. That's what the restrictions are on this equation. Otherwise, just make sure you know this formula, a times b to the x power. Now, like I just said, when b is greater than 1, that's when we're going to be dealing with exponential growth. If b is between 0 and 1, so we have a decimal, that's what we're going to talk about in a future video, that represents exponential decay. So let's look at some examples, some real-life problems, scenarios that would, some scenarios where we'd be using exponential growth. One of those would be with dealing with the population increase. So let's look at the population increase of some rabbits. So here it says rabbit reproduction is an example of exponential growth. For example, in 1859, there were 24 rabbits that were introduced to an area in Australia. However, they reproduced so quickly that 20 years later, they were referred to as a gray carpet on the continent. Because a pair of rabbits can produce an average of 7 surviving rabbits a year, you can estimate that the rabbit population multiplied by a factor of 7 halves, or 3.5 each year. Because there's 7 rabbits being produced from every 2 rabbits, so the growth factor would be 3.5. We're going to let A, your initial amount, be 24, because that's what we started out with. We introduced in the year 1859, they introduced 24 rabbits to the continent. And your growth factor, again, is going to be 3.5. And n is going to represent the number of years after 1859. So we can represent this by an equation by saying 24 times 3.5 to the nth power. Now, if I were to put different numbers in here for n, I would get these values from this table. Now, granted, this is a model, so this does not mean that they did not go around after 1 year and count all those rabbits to find that there's exactly 84 rabbits. It's just saying that on average, if every 2 rabbits produce 7 rabbits, that means that we'd have a growth rate of 3.5. Now, granted, there might be some scenarios sometimes where more than 7 rabbits are born, or maybe even sometimes where less than 7 rabbits are born, but that represents an average. And also there's going to be rabbits that are going to die from disease or falling off a cliff or being eaten by an alligator or whatever the case is. So there's going to be some dying off, but they're always going to be growing. So this represents a model, so it gives us an estimate of about how many rabbits were there on the continent of Australia after a certain amount of time. So you can see here that we started out with 24 rabbits after no time has passed. But only 5 years later, we were already up to 12,605 rabbits, or approximately 12,600 rabbits, give or take some. And after 10 years, it's already gone up to over 6.5 million rabbits. So if we use this model, we would get 6,620,514. So it'd be safe to assume that there'd be over 6.5 million rabbits by 10 years since they were first introduced. So that's why they were called the gray carpet. Now you can see what the graph looks like. So this is not right on the x-axis. This point here is above the x-axis, but at 24. For the y. After 1 year, you can see that it's gone up a little bit. After 2 years, you can see it's gone up more. After 3 years, or after another year here, we can see that it increases by a lot. And by 4 years, it doesn't even fit on the graph. Oops. So you can see that when we have something increasing exponentially, as x increases, the distance here between y is going to get even greater and greater. So this is what we call an exponential curve. Now, when you're dealing with exponential functions, the range is always going to be the positive real numbers, or The way I like to write it is like this. So the range is going to be where y is greater than 0. And the x-axis always acts as a horizontal asymptote. Now we talked about asymptotes back in, I believe it was chapter 2 or 3. But that's where these values, these points that we graph aren't touching the x-axis. That makes the x-axis a horizontal asymptote. Now, for the purpose of these problems, we're not going to be doing parts B and C because in order for us to do part B, we'd have to, part B is asking us to figure out how long it would take to get to 5,000 rabbits. So the only way to do that, one of the only ways to do that, or the best way to do that, would be to use logarithms, and we haven't learned about that yet. Granted, we could use graphs, but it can be a little confusing. So for right now, I just want to make sure that we understand how to set up these equations and how to use them. So here they asked us to estimate the number of rabbits after 2 years and 3 months. Now let's talk about that for a second. That is not equal to 2.3. We need to convert that. We do need to convert it to a decimal, but that's not your answer. Now let's think about that for a second. 2 years and 3 months is, well, there's 12 months in a year, so 3 months would be 3/12 of a year, or that would reduce to 1/4. And that, as a decimal, would be 2.25. So that's what we're going to use for your time. So your number of rabbits would be 24 times 3.5. Our exponent's going to be 2.25 rabbits. Or 2.25 years, rather. So to figure out how many total rabbits there would be, we'd plug this in on your calculator. Now, a little note about your calculator here. Just as a review, to be able to access exponents, we need to use the caret button. So it would be 24 times, what was our growth rate? 24 times 3.5. Oops. And our exponent's going to be 2.25. So your exponent button that you're looking for is that caret button. So go ahead and type this all in at once and hit enter. And you get about approximately, now we're not going to say 42 or 402.1 rabbits. There's not going to be 0.1 rabbits rolling around. It's going to be just 402 approximately. And since we're estimating 2, you could have even said approximately 400 rabbits, and that would have been fine. This doesn't just apply to rabbits, it also applies to bacteria. Here's a situation involving a certain type of bacteria that doubles in population every hour. Suppose an experiment began with 300 of these bacteria. Now, we could have come up with this equation on our own, because we know that we began with 300 bacteria. So there's your initial amount. We know that it doubles every hour. So that means that it's being multiplied by 2. So your growth rate is 2. We're starting out with 300. So that would be your equation. Your initial amount times your growth rate to the t, in this case, as your exponent, where t is the number of hours. So for part A, for 3.5 hours to predict how much bacteria there'd be, we would take 300 times 2 to the 3.5 power. And when you do that on your calculator, we're going to get, let's see here, 300 times 2 to the 3.5 gives us approximately 3,394 bacteria. Or if you would have said 3,400 bacteria, that would have been acceptable as well. Now, with these last couple of examples, we're going to come up with the equation. So here it says the speed of a supercomputer is measured in teraflops, or trillions of floating point operations per second. In the year 2005, the Blue Gene/L supercomputer recorded a speed of 280.6 teraflops. Over the last 30 years, the speed of the fastest supercomputers has been growing about 78% per year. Suppose that this growth rate continues, and let C of x be the speed in teraflops of the fastest supercomputer x years after 2005. So we want to write a formula for C of x. So to write our formula, we start out with your initial amount. What are you starting out with? Well, we're starting out with 280.6 teraflops. Now your growth rate. Let's talk about percents for a second. When it's an example of percents that are increasing, we're going to add the percent. Then we're going to change it to a decimal. Here's why. That's 78%. It's growing. If I would just use 0.78, remember my growth rate here, my value for B, has to be greater than 1. Well, 0.78 or 78% or 0.78 is not bigger than 1. Well, that's because it's growing, so it's increasing. So it's going to have 100% of what there was before plus another 78% more. So we would take the 100% of what we had originally plus 78% more, which would give you 178%, which as a decimal would be 1.78. So you always move the decimal place 2 places to get the decimal, or to change a percent to a decimal. So we have 1.78, and your x represents the number of years after 2005. There's your equation. So if they asked you to find what would the teraflops be in the year 2015, we would put 10 in there for x, because 2015 would be 10 years after 2005. So why don't you guys try this last example on your own to try to come up with this equation. So why don't you pause the video and hit play when you're ready to check your answer. Okay, so why don't you check to see what we got here. So this time we're dealing with the population of California in the year 2000. That's kind of our base amount. That's what we're basing everything on here, is 33,871,648. So 33 million, I should say. 871,648. That's your initial amount. It's growing by 1.3% a year. Well, that means that we're going to take 100% plus another 1.3% each year, or 101.3%, which as a decimal is 1.013. And x represents the number of years after the year 2000. So that would be your equation. So that's pretty much it. So the key from this lesson is to make sure that you know this formula. A times b to the x power, where your initial amount is what you're starting out with, your original amount. That's your value for A. Your growth factor is always going to be greater than 1 when we're dealing with exponential growth. So make sure that when you're dealing with percents that you add 100 and then change it to a decimal. So with that, good luck on your assignment.